Hello, for communications and network 1 class today, Ajahn Usla will talk about how to decode the cyclic code using chip register circuit. Okay, I didn't write the cyclic code here because all the encoding and the decodings are done for cyclic codes only in this class. Okay, again, to decode, we will compute the remainder of the receive sequence over the generator sequence, okay, to see if the receive sequence R is divisible by the generator sequence or not. Okay, so how to do this? We feed the receive sequence, okay, R into the chip register circuit. This is to decode, okay. In the past, when we want to encode, we feed the data sequence U into the chip register circuit. It's actually the same register circuit structure, okay, with a different into the input, okay, of the input. Now, let's compare clearly, okay. To decode, we feed from the left-hand side, okay, of the chip register circuit, okay. The result in the chip register, okay, after the last bit is shipped in is called syndrome S, vector S, and we check if the vector S is equal to 0 vector or not. If S equal to 0, okay, assume no error, as we have done before. If S not equal to 0, we know that the receive sequence have errors, okay, one or many errors, okay. To encode, okay, in the last slide, okay, so we feed U from the right hand side, okay, of the chip register circuit, okay, and the result after the last bit of U is shipped in is called parity check sequence B, right? And then we have the code word equal to 2 to the n minus k multiplied by U plus B. So this is your code word. Okay, so encode and decode, they are different, but they use the same structure of the chip register circuit. Okay, let's see an example. I give you the same examples as before and try to keep the same notation. So most of it is on the left. Okay, and we have 7-bit, okay. Okay, and you want to decode the chip the receive sequence with the chip register circuit. To make it easier, I will change this into generator polynomial. So x cubed plus x plus 1, right? And to fit in with the way that we will draw the circuit, I will reverse the order here. So it's 1 plus x cubed, which is still gx, okay. A minus k equal to degree of gx equal to 3. So we have and equal to the number of boxes inside of the chip register circuit. So I have 3 boxes here. Okay, then this is x to the 0. X, we have the x term, right? We don't have x squared, so nothing here, no feedback. And we have x cubed here. Okay, and this is the feedback line. Now, I told you input is from the left. So I have R coming in, and then since you have the 2 inputs coming in, right? So you must have model 2 addition or the XOR gate, okay, into the next box, okay, like this. If you have nothing feedback, okay, then you just shift directly. Again, this is also shipped directly, okay. Be careful of the arrow direction. We have R is, again, most communities come in first, so 1 1 1 0 1 0 0. This is most significant bit, okay, coming in first. Your initial, okay, all zeros in the chip register, okay, so all 0. And then be careful when you have a feedback here. So I put a line here so that I have to be careful. So the first one coming in, feedback is 0, okay. So 1 plus 0 is 1. So I get 1 here. Feedback is 0, right? So I just get 0, 0 here. Okay. Next, I have 1 in, feedback still 0. So I get 1 here. Feedback is 0, I get the same. Okay. Then again, feedback is 0. I get 1 in, I get 1. And then this chipped. Now, at this point, our feedback will become 1. Feedback will become 1. Okay. But input is 0. 1 plus 0 is 1, right? So I get 1. Feedback is 1. So 1 plus 1 is 0. This is 1. Okay. Then this one, sorry, this is, okay. This one, feedback, input is 1 now. Okay. 1 plus 1 is 0. Okay. 1 plus 1 is 0. And then this one shift. Okay. 0 feedback. Okay. Plus 0 is 0, 0, 0. And then 0 feedback plus 0 is 0, 0, 0. Okay. So this is your answer. This is your syndrome. Okay. This is x squared, x to the 0. Okay. Because most of it is on the right. So your syndrome is 0 vector, and you assume no error. Assume no error. Okay. Now, this is the same picture as what I just draw, but in case you cannot read my handwriting, okay? Anyway, so this is the most significant bit, okay? And we have 7 bits of R, right? So most significant come in first, and then after the first bit come in, then you have 6 left, okay? And then this one come in, you have 5 left, okay? Like this. If you notice, okay, you can see that since the chip register circuit at first initialized with all zeros, and we have 3-bit zeros here, so all the feedback, the first 3 feedback will be all zeros. So actually, the first 3 bits here will become the first 3 bits after the first 3 shift, okay? So this is the most significant bit, okay? So you can use this as a checkpoint, okay, to make sure that you do it correctly, because the first 3 zeros are feedback as zeros, okay. So the first 3 bit will be the result, okay, after the 3 shift, okay. Anyway, the syndrome is all 0 again. This is coefficient, most significant bit on the right, okay. And the first 4 bit will be output as data, okay, same as the last 2 examples. How to do this? You can use the same method as before, but you can also use this, okay, looking at the chip register, okay. I have n equal to 7 bits, okay. N minus k equal to number of box in the circuit, okay. So we have n minus k equal to 3 box, okay, equal to 3 bits, okay, in this case, okay. And n equal to 7 bit. So what is k? K equal to 4, right? So it's a 7-fold code. So you have 7-fold code, so data are 4 bit. And what is your R? R is 1110, 100, and this is most significant bit. So this is your data, okay. Output as data with this is most significant bit of data, okay. So this is done, okay. You decode it, you found that the received sequence has no errors, okay, and you output the data to the users, okay. Now for the next slide, I will teach you how to correct simple very simple error pattern, okay, like single bit errors, okay. So this is the end of the slide. Thank you very much.